So today we will see the elements of VHDL. Last time we had studied the anatomy of VHDL. So today we will start with the elements of VHDL. This is basically assuming that you have not ever studied VHDL. So I am starting right from scratch. As we have already seen, the basic building blocks are library declarations, entity, architecture, and configuration. We have also seen this a little bit more detailed kind of figure, where I said that there are three possible ways in which you can write the architecture. In fact, four, if you consider the mixed mode also, that is the data flow, behavioral, and the structural, and maybe a combination of structural and behavioral both. Okay, we'll start with the library. What is a library in VHDL? It is a collection of compiled VHDL units. All of you know the importance of library because ultimately it enables the sharing of compiled designs. And of course, we can treat the smaller designs as black boxes, which are actually the source codes from different users. Commonly used functions, procedures, user data types can be compiled into the user-defined library, and you can use them with all your designs. But the only thing is that you have to declare. The library has to be declared before each entity declaration. This is a very, very important step. Now, this is very much similar to the conventional programming languages. For example, in C or Turbo C kind of environment, you declare the libraries as stdio.in and so on and so forth, right? So in a similar way, these libraries have to be declared right in the beginning. To declare a library, that is, you have to make it visible to the design. Only two lines of code are needed, one containing the name of the library and the other the use clause. Okay, we'll see the use clause in more details. But the structure of the library will be like this, that the library contains what is called as a package. Now in packages, you can have different functions, procedures, types, constants, and components. Remember, you can design your own components and keep them in a package, which in turn will be kept in a library. This is the library syntax. The method which I follow is that all the keywords I use with black font color and other font colors for different the user provided names. So here in this case, the two statements that you have to write over there are library, mention the library name with a semicolon, delimited with a semicolon, and then use that library. Another directive is use the library name dot package name dot package parts. Again, terminate with a semicolon. A very simple way of declaring the library to be used. So the example here is, now most of the times we use this library IEEE. So in library IEEE, there is a package called as std_logic_1164. And in that package, all whatever are the things given in that particular package will be accessible if you write this, if you append it with .all. Okay. So that all parts. Package parts, those are the package parts. So library IEEE, use IEEE.std_logic_1164.all. Okay. Or you can have your own user defined library, which is called as work, and you can use it like this, like library work, use work.all. Remember, this double dash in VHDL indicates a comment. So whatever is written after a double dash will be ignored by the compiler. These are the library details. You can just go through this. There are various different types of libraries and the packages therein. So in IEEE, basically IEEE package is a huge package. In that you have library. In that library you have the package called as math_complex, and you have all the definitions over there in all. or the complex mathematical operators, functions and operators. Then IEEE.math_real, again a similar way, IEEE.numeric_bit. So in this particular bit, which is very essential for us, the basic element type is bit. Okay. So two numeric types are defined as unsigned and signed. Okay. Then IEEE.numeric_std.all. Again, this is numeric type. Basic element is std_logic. Okay. And this library details you can just go through. I'm going to share the handouts also. So all these are the library details. Out of that, this IEEE.std_logic_1164.all is very, very important. Okay, because it defines the standard for the designers to use in describing the interconnection data types. Okay, specifically used for VHDL modeling, which is the basic theme of our course. It actually defines the multi-value logic. We already have seen the multi-value last time. So all is concerned with that. Again, these are the other library, other package types. The next important part in VHDL is the entity. It is actually the design's interface to the external circuitry. Just a moment. One and only one entity. So VHDL design will have whatever design you have will have only one entity. Please remember that. And this entity also can be used as a component in other entities, but of course after being compiled into the library. How to declare the entity is what we are going to see. It defines the input and the output ports. So this is only the package. Okay, the package of the IC, for example. Okay, and it declares only the input and the output. Name of this entity can be anything other than the VHDL reserved word. Each port in the port list must be allotted. So you have to allot a certain procedure is there. Each port is in the port list will be allotted with a name, a mode, and data and a type. So there are three parts for the declaration of the port. One is the name, other is the mode, which is actually deciding the data flow direction, and the type of that particular port. Code should be well documented with comments, and of course make sure that you use self-explanatory names for those function names basically, so that it will not be confusing later on. Code should be well documented with comments at the end of line, providing additional information about the signal. So exactly what that signal does, we're going to see there are various different data types and all those things, and the very important object that is called as a signal and a variable. So these are the two important objects that we are going to see later on. This is the syntax for entity, entity name, entity underscore name, then port. Okay, so you have to write that in a starting bracket and an end bracket. And the port name, signal, mode, and signal type, terminated with a semicolon. So each port will be separated by a semicolon. But look at the last port only. The last port, you don't have a semicolon, you have a closing bracket followed by the semicolon. So this is the common mistake committed by beginners, that they write semicolon here and then they land up with a lot of problems. Okay, and then end entity name, again terminated by a semicolon. Is the entity declaration clear to all of you?
Yes, sir.
Right?
Yes, sir.
Okay. Then let us talk a little bit more about the modes. There are 4 different modes. That is the data flow direction: mode in, mode out, mode in out, and mode buffer. Okay. The mode actually indicates whether or not the port can be read from within the entity. So actually it indicates what is the driver direction. Driver is nothing but some kind of a buffer, and you know that if I use only one buffer, I can have only one direction. For example, here mode in, the value can be read from but not assigned to. Now this is from the perspective of the entity and not from the external source. Okay, so assume that you are the entity and somebody has declared port A as in type, that is mode is in. In that case, only you can read from it. You cannot write onto that port. Okay, because the driver resides outside the entity. That is the basic idea, and this driver is nothing but a buffer. Okay, this is just to enhance the drive capability, source capability, or sync capability. The simplest buffer that you can design is what? Which circuit? Guys, the simplest mode, the simplest buffer that you can design is with an operational amplifier in the which mode?
Forward non-inverted mode.
Non-inverted. No, we don't want amplification. So it will be the voltage follower mode. If you remember the voltage follower mode,
Yes.
voltage follower configuration, where input impedance is supposed to be very high and output impedance is supposed to be very low. Okay, that actually enhances the syncing and the sourcing capability. For that, you should understand what is the loading effect. Do you have any idea of the loading effect?
Yes, the resistance, input and output resistance, like output resistance
What
of
is loading effect?
previous.
What exactly do you mean by loading effect? No?
The output resistance of previous stage, uh, and and the input resistance of the next stage. Like they have to be.
Yes, we are very close.
So they should match for maximum power to be transferred to
Match? No. Maximum power transfer theorem is different. They should, you should not say they should be there matched. We are not talking about power transfer here. We are talking about the voltage loading effect. So what will be the picture?
output resistance should be high and the input resistance of next stage should be output resistance should be low.
Yes, that is all right. But
And
I'll give you a simple explanation over here. And that is, okay, let us talk about such a kind of circuit. A simple circuit. And I'm connecting a load. Let us not connect the load right now. So you are having 10 volts here. This is 5K and this is 5K. What will be the voltage here? What will be the voltage?
5 volts.
So it is 10 volts multiplied by 5K
For
divided by
5 plus
5K
5
plus
plus
5.
5.
The simple potential divider. So you get 5 volts.
5 volts.
But this is open circuit voltage. Now if I connect a load, and unfortunately that again is of 5K, will this voltage be any longer 5 volts?
No.
What is the new voltage then?
5K.
Calculate the new voltage. Be ready with your calculators. Anytime I may ask such questions. Are you able to calculate the output voltage?
Yes, sir.
Do it. How will you calculate that? Aditya is not answering questions. Aditya.
Wait a minute. हाँ एक मिनट सर.
Why is it taking so long?
Ten into 2.5 upon 7.5.
Yes. How much? Tell me.
10 into that will be 6.66 volts.
How can it be 6.66 volts? This will be 10 multiplied by. Now, what is the effective resistance now of this branch? 2.5K
2.5
divided by 2.5K
plus
plus 5K. So this is how much? 10 into 2.5K by 7.5K. So this is 10 by 3.
3.33, sorry.
So it will be 3.33 volts, which is a bad thing. A bad thing has happened, no? You
Yes.
started with
It has
the
reduced.
saying, okay, I want 5 volts, but as soon as you connected the load, the voltage dropped to 3.33 volts. What is the significance of this? If your load is TTL, this will never work, isn't it?
Yes.
So what can you do?
Yes.
What is the remedy? The remedy is, let us say now,
Increase the value.
instead of yes, what is the remedy?
Increase the value of the load resistance.
Load is out of your control.
Okay.
The customers will say, okay, this is my load. You cannot change it. Now try with this. Find out output voltage now. How much do you get? What is the new output voltage? Yes?
4.95.
4.95.
95.
Is the situation improved?
Yes.
Definitely. So what has happened? If you look carefully, this is the input impedance. The output impedance of the network. And then you have the load connected to it. So in our case, what is the output impedance? In the new case, network output impedance, if this is 100 ohms, this is 100 ohms. What is the output impedance? Looking from this terminal. Yes, tell me. Come on. What is the output impedance?
5.
What?
50 ohms.
How much?
50 ohms.
50 ohms. That is absolutely correct. How do you get that?
So both are in series.
You simply have to remove this.
Grounded. Yeah.
And
Grounded. Both comes in parallel.
So now you get 50 ohms. Now this is our 50K. So do you see any relationship? Okay, earlier when it was 5K, what was the output impedance? 2.5K, right?
2.5K.
So this was the 2.5K was the output resistance and the load was 5K. Here now the output impedance is 50 ohms and the load is 5K. So do you see any relationship? We can say that the loading will be minimum. Remember, loading can. Are you getting this?
Yes, sir.
And loading effect is a very, very important phenomenon because in every hardware circuit you will come across some variant of this loading effect. Okay? So if you want to avoid, or let us say if you want to minimize the loading effect, you must have the output impedance very much less than the load or the impedance of the next stage. Okay? Now if you have an amplifier, voltage amplifier to be more specific, and you have a source like this, some kind of, okay, this is the source resistance and this is your input impedance, this is your output impedance, and you have the load. So in order to avoid the, in order to minimize the loading effect, we have already seen this. If this is RL, then your ZO should be very much less than RL is fine. We have proved that. But what about this? What about the input side? Again, there will be loading at the input side because of the input impedance of the amplifier, no? So
Yes.
similar line, I should say RS should be very much small as compared to Zin, or Zin should be very high as compared to RS. Clear?
Yes, sir.
So
Yes, sir.
ideal voltage amplifier will always have what?
High input
In
impedance,
equal to infinity, and
0.
0.
this is going to be an ideal voltage amplifier. But we don't have ideal voltage amplifiers, we have practical voltage amplifiers. So always, whenever you design voltage amplifiers, I'm talking specifically of voltage amplifiers, your input impedance should be as high as possible and output impedance should be as
As low as
low as possible. A very simple buffer to do that will be take an operational amplifier and use it like this. This actually is most of the times drawn like this as a buffer. Okay, now if I apply a signal over here, will it be available at this end? Yes or no? Or in simple plain words, is this a unidirectional device or a bidirectional device?
only input is required, so
Yes, so it
unidirectional
is
at
a
the moment.
unidirectional device. ठीक है ना? So naturally, when such a kind of buffer or driver, it is also called as driver, is outside the entity can only read from it. It cannot write anything from it, write anything onto it. Okay? See, you will be surprised, but VHDL is not just to be taught like a conventional programming language. you have to have a lot of hardware basics all the way along. Okay, that is how VHDL is different from the conventional programming language. Okay, is that fine?
Yeah, yes.
Okay, so
Yes,
now
sir.
have you understood the concept of mode in at least?
Yes, sir.
Okay, and then we have said that what type. So it belongs to the STD logic type. So I've declared a port, in fact, something like a pin, and you can have A, the name of that pin. So it will be the name of the pin, and it will be an input port. That is how I declare it. Similarly, I have mode out. Remember again that the driver is inside the entity. So the value can be written, okay, assigned by the entity, but it cannot read from that port. Is that clear? Guys,
Yes, sir.
Yes, sir. Yes, sir.
in a similar way, we have mode in out. Now, this is a special type of a port where you have drivers residing both inside and outside the entity. Okay, and naturally, the value can be assigned to as well as read from the entity. Does not mean that you have to use it frequently. We'll see what is the problem with that. Okay, so if you are okay, so it can read back. Okay, the entity can read back whatever is it has written. Now this is to be avoided again. For many times it is to be avoided. This is the example of entity. As you can see, it resembles the pinout. It exactly is the pinout. Okay, what is there inside we don't know right now. Just the interface. The interface is like 1, 2, 3 number of pins, and then you have the functions over here, like the names of those pins. Okay, so how do you declare such a kind of entity? Entity, for example, AND gate is port 1A, 2A, 3A, 4A, all are in type, in mode in and STD logic type. Similarly, 1B, 2B, 3B, 4B are also in and STD logic type, whereas 1Y, 2Y, 3Y, and 4Y are mode out STD logic type. Now, STD logic type means what? We've already seen that STD underscore logic. What do you mean by that? It is actually the multi-valued logic. So apart from 0, 1 high impedance, it has got the weak high, the weak low, okay, uninitialized and all such other values also. This is the example, a more realistic example. For example, if I want to design an ALU, arithmetic logic unit, in that case, I'll do it this way. Okay, now the variation that you will see here is that instead of a single pin, I am declaring a couple of pins here. So we call it as a bus. So how to declare that? You can declare it as a, instead of STD logic, STD underscore logic, you declare it as STD underscore logic underscore vector. This is another important keyword. And then what is the bus width? 3 down to 0 means it is a 4-bit bus. Okay, so this in 1 is a 4-bit bus, in 2 also is a 4-bit bus, opcell is again a 4-bit bus. Okay, the result is again a 4-bit bus, and so on and so forth. Have you understood this? So how to declare the single pin and bus? Yes, have you understood?
Yes.
Fairly easy.
Yeah.
Then coming to architecture. Okay, so what does architecture do? It defines the behavior or the function or the relationship between input and output of an entity. Okay, so in simple plain words, it is the let us say the engine, basic engine of our device. Okay, here it will have all the functionality being written. What is the syntax? Syntax is architecture, the name of the architecture of. Now it has to be associated with the entity name. So this architecture belongs to which entity? That is the entity name is. There will be a couple of declarations if you want. They are optional, of course. We'll see later on what these declarations are. Then it always starts with a begin. Then you can write all concurrent statements only. From begin to end, you can write only concurrent statements. This is very, very important for you to understand. What do you mean by concurrent statements? As again sequential statements we have already seen. Yes or no? What do you mean by concurrent statements?
Parallel execution.
They are executed.
Yes, they are executed simultaneously. Okay. So such kinds of statements will be
Yes, sir.
executed simultaneously or parallelly. That is called as concurrent statements. So in architecture after begin and before end, only concurrent statements are allowed. This is one important thing that is required to be remembered. Architecture can contain only concurrent statements. Design can be described in an architecture using various levels of abstraction. We have already seen the levels of abstraction. So you can choose any one method. Entity can have more than one architectures. That is what we have also seen in the anatomy of VHDL, because the function can be implemented in a number of ways simply. Remember that there can be no architecture without an entity. So this entity is unique. Architectures can be many, but architecture cannot exist without an entity. In simple layman's term, it's like the soul of a person and the body of a person. Are you able to understand that?
Yes, sir.
Okay. So in order to function properly, soul has to have a body. All right. So in a simple plain words, architecture is the soul of your, let us say, the entire design. What are the various different ways in which you can define the architectures? One is the behavioral way. We've already seen the three types, and the fourth one, which is a mix of any two. So behavioral, it is a high level description. So highest level of abstraction. So means we are hiding so many things. I can write this in such a way that I need not really go into the details. Okay. So it will contain a set of assignment statements to represent the behavior. There is no need to focus on the gate level implementation. A very simple example is architecture of the, this is the architecture name and this is the entity. Okay. Now these statements are not concurrent. So you'll be again perplexed. How can I write concurrent statements, non-concurrent statements in the architecture? So for that we have one very interesting way, or let us say interesting construct, and that is called as a process. We are going to see in more details about this. So process itself is a concurrent statement. So whatever is there inside the process may be sequential. Okay, but the process itself is a concurrent statement. Okay, so what we are saying here is if A is equal to 1 and B equal to 1, then C is equal to is assigned 1, else C is assigned 0. The assignment operator is like this always. Remember that. What does it mean? If my input A is 1 and B is 1, then only C is 1. Otherwise, C is equal to 0. So does it have any reference to the gate, inbuilt gate or whatever it is? It is not having any reference. Any gate level implementation is not mentioned here. So we are hiding that, we are abstracting it, and then we are saying that, okay, but this actually behaves like an AND gate. If it behaves as an AND gate, naturally, this is the behavioral description. So this is the way in which you can write the behavioral model. Understood? We are going to see what this process A comma B is later on. But for the time being, understand one thing, that process is a concurrent statement on its own. And inside the process, you are allowed to write sequential statements, because this construct, if, then, else, and if, it is a sequential construct. We are going to see that. Clearly, that one simple line, I can say that C is assigned A and B, and is an inbuilt keyword. Okay, and that is it. So once you write this, you don't have to do anything else. Your AND gate is ready. Okay? So this is the data flow technique. Another is the structural technique. Now AND gate itself is a smallest component. So I have to take a different example here. The component from libraries can be connected together. These designs are hierarchical. Each component can be individually simulated, and it makes use of what is called as a component instantiation. This is a very important process, specifically in the structural and the mixed mode kind of program, mixed mode kind of modeling. Okay. For example, your top level design. Now there are certain levels. Every time you design anything in VHDL, that is the top level. Even if it is an AND gate, it becomes, you're defining it as as the top level, and then you're defining the code and everything like that. Okay. Now what you can do is, we are supposed to design what is called as a full adder. Full adder is composed of 2 half adders and 1 OR gate. Now these are individual components which are already available in our library. Now this structural method gives you a flexibility to import all the components, which is, the process is called as a component instantiation. It simply imports these components from the libraries, and then your job is to only connect it. Okay, your job is to only connect it. We'll see more about this in greater details when we study component instantiation. So this is the third type. Fourth type can be a mixed mode of data flow and structure. Okay, or any other combination. Then the last part is the configurations. We have seen that there are so many number of architectures available. Now, which architecture exactly to use with the entity, you are supposed to tell the compiler and the elaboration phase what architecture you want to use. For that, there is another construct which is called as a configuration. So configuration, you can name the configuration for that particular entity name and for the architecture name, because we can have different architectures. Entity name is only one, but architectures can be different. And for, so this actually indicates which architecture is to be used while compiling. Okay. We'll go in for the language elements immediately. Okay, is the slide visible to all of you? Guys?
No, sir.
Neither.
Yes, sir. Yes.
It's
No.
one. Yeah. I think it should be available. Okay. So the very first thing that we should understand is that VHDL is a strongly typed language. What do you mean by strongly typed? Let me ask you this first. Does it mean that the designer has to apply force on the keyboard while typing? Does it mean that? What do you mean
No,
by
sir.
strongly typed? It simply means that you have to declare the data type before using it. You cannot declare the data type on the fly. Just like C language, we declare something like float f, int whatever I. Okay, that declaration has to be done before you use the data type. So that is such a kind of language is called as a strongly typed language. Understood? VHDL is not case sensitive. So you can use lowercase as well as uppercase. It doesn't have any effect on that. Okay. But avoid mixing the cases. Okay. Many times the good programming practice says that avoid the mixing of the cases. VHDL supports a wide variety of data types and operators. So what are these data types and operators? These are the objects, operators, and aggregates. We'll see that. So what are the objects? They are the used to represent and store the data in the design being described. Object contains a value of specific type. Okay. So you've already seen the signal, the class. So you have the class, object, and data type. These are the three essential things. So whenever I want to declare something, declare some kind of a variable. Well, variable is not a proper word to be used here, but in the context of the conventional programming languages, if I want to declare a variable, what should I do? In VHDL, it is not directly that you declare something as some data type and then give the name to that variable. It's not that way. What you have to do is you have to have three different parameters. One is the class itself. What is the class of that? Let us say variable. Object, the name of the object, and its data type. So there is a certain way in which you have to declare the data type. So this particular example results in an object which is called as count, and it holds an integer value, and it belongs to the class signal. We are going to see what these classes are. Name given to the object is called as identifier. So this count here is the identifier. Again, word of caution, do not use the reserved keywords as the identifiers. So each object has a data type and class. Class indicates how the object is used in the module and what can be done with that object. Type indicates what type of data the object can contain. Okay, these are distinct parameters you can see here. So each object belongs to one of the following classes. So let us see what are the various different classes here. The class can be constant, signal, variable, and files. These are the four classes which are valid in VHDL. Okay, constant, signal, variable, and file. So this particular example, in this particular example, the object belongs to the class signal. Okay. Then what are the data types? In order to write VHDL code efficiently, we have to study the specification and use of the data types. So the data types available in VHDL are predefined, user-defined, subtypes, arrays, port arrays, records, signed and unsigned. So these are the various different data types. Here again, this table gives you the libraries and the type functions. Okay, so we have IEEE 1164 std_logic. The library is IEEE, and the functions therein or the classes therein are std underscore logic and std underscore u logic. We'll see with an example. So here, bit, if I want to declare, so the very first example, if I want to declare it like this, bit or bit vector, doesn't matter what it is at this point, whether it is a single pin or it's a bus. Right now we don't know. So bit actually belongs to, or rather let us say, and bit vector, both these have only two levels, 0 and 1. It is only a two-level logic. Remember that. It is not like IEEE. It's not like 1164 std underscore logic. Okay. So this bit type is different. It can hold only, or it can take up only two values, 0 and 1. Example of declaring this bit type is, this is the type, this is the class. So this X is the name of the object, belongs to class, and it is of data type bit. So X will contain only either 0 or 1. Similarly, a bus. So this is a 4-bit bus. All right. This is another 8-bit bus. Okay. Now you see, there are two ways in which you can declare the vectors. These two distinct ways: 3 down to 0, 3 down to 0, or 0 to 7. Now don't mix up those things. Use either this convention or this convention. Because here the MSB and LSB positions are reversed. That you have to understand carefully. So in this case, y is 4-bit vector. So if I define y like this, so in this case it will be y0, y1, y2, y3. So it will look like this. This is y0. And this is going to be the MSB. This is going to be the LSB. It is not here in this case. It's not like that. So if I have this as W0, here it will start with W0, W1, W2, W3, and W7 finally. W4, 5, 6, and 7. So here in this case, this will be the MSB. So the way in which you declare, this will be the LSB. Okay. So follow any one method. Don't mix it up. Clear? Is this fine?
Yes.
Are you all following whatever I'm saying?
Yes, sir.
Yes.
Okay. Now assignment operator is already we have seen. Well, not formally, but here it is now. To assign a value to the signal, use this operator. So remember always that has to be a less than or equal to sign. Okay, this becomes the assignment operator for signal class. There is another type we'll see later on how to assign to that. Okay, so here X is a single bit kind of a object which belong to the class signal and bit type, of course, and that when I do like this, I mean that X is a single bit signal whose value is 1. Okay. When I want to assign something to a vector or a bus, I have to use it like this. See the difference? There is a single quote here and there are double quotes here. This is the major difference. And again, the possible mistake to be committed by beginners. All right. Have you understood this?
Yes, sir.
So here
Yes,
is
sir.
this case. Yes. Any doubt? Any question?
No, sir.
Okay. See here again, which is the MSB, which is the LSB. The declaration is different. W, which we have already declared in a particular way, this was the MSB. Here in this case, this is the MSB. Why? Because earlier it was declared in a different way. 3 down to 0 and 0 to 7. Okay. Then let us revisit the std underscore logic, 8 valued logic. It is the 8 valued logic. X is unknown, 0 is low, 1 is high. This is high impedance. This is weak unknown. This is weak low, weak high, and don't care. Okay. So you'll ask me the question, why forcing? What do you mean by forcing? Whenever we want to assert anything, for example, in case of any logic circuit, if I want to assign a value, we are actually forcing the voltage. Okay. For example, if you are having an AND gate, so what you are doing here is when you are connecting 0, or let us say connecting 1 here, what are you actually doing? You are actually forcing the voltage here, making this 0. In this case, you are forcing it to be some, if it is TTL, somewhere around 4.5 to 5 volts. So you're actually, the concept here is that your assignment is in terms of forcing the voltage. Okay, that is the reason why it is called as forcing. Okay. Now again, I urge all of you to have a separate page, last page of your notebook, and make 2 columns. Okay, I'm just using the table from here. Okay, as and when we go through the course, we are going to see which of the objects, which of the constructs, which of the elements are synthesizable or not synthesizable. This is very, very important, because ultimately you have to make everything in the terms of synthesizable. If it is not synthesizable, it remains only a fancy item which can be only simulated. That also functionally. Okay. So make a use the last page of your notebook and make 2 columns, synthesizable and non-synthesizable. As and when we collect, as and when I say in the class, go on adding those elements in this list. So at the end of the course, you are going to get a list of synthesizable and non-synthesizable constructs or elements. Is that fine? Have you understood what you are supposed to do?
Yes, sir.
Okay. So here again, that brings us to, this is synthesizable, 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 synthesizable. These are not synthesizable. So X, 0, 1, Z, they are synthesizable. W, L, H, and dash, that is don't care, are not synthesizable. Remember that. And update your table. What do you mean by synthesis or synthesizable? Yes. It means that there are hardware counterparts available, or you can realize that. Okay. Whereas you cannot realize unknown. What do you mean by unknown? How do you realize it in hardware? Weak low, how do you do that? Weak high, don't care. You can't do that. So there are a certain set of things that you should know which are synthesizable and non-synthesizable. Okay, so this is the example of std underscore logic type. Signal is again, class is again signal, and the object name is x. So x is declared as 1-digit scalar signal of type std underscore logic. So once it is declared as std underscore logic, it can take any of these 8 values. In a similar way, you have the declaration of std logic vector. So this is a 4-bit bus again. All right, but now the data type is std underscore logic. Earlier it was bit or bit vector. Now here it is std logic vector. Okay, signal again, the way in which it is described, declared is different. And there is one more thing which you have to see. So if I want to initialize any vector, I can do it with this particular operator, colon and equal to, but that also only at the time of declaration. Okay. By the way, what is high impedance and why it is synthesizable? What do you mean by high impedance? Why high impedance is required in the first place? Z. Why do you require high impedance state? Basic question.
It draws very less current.
No. Okay, I put this as a question. You can answer it in the next question. Okay. Yes. Try to get the information why. What is the requirement of high impedance state? And next lecture, I will ask you the same question at the beginning. Anyways, I think we have already exhausted the time, so I'll stop here for today, and we'll continue tomorrow. Another thing, probably your timetable is also going to get slightly changed. So we will be meeting on Fridays and Saturdays. Saturdays, I think we'll be having 2 lectures in tandem, that is back to back. We won't be having any lectures on Sunday. All right, please. Of course, you have to wait for the formal notification, but this is just a tentative thing. All right. So we'll stop here for today. Any doubts? Any questions?
No, sir.
No, sir.
No. ठीक है. We will stop here and end the meeting.